Here we are for lesson 3. We're looking at multiplying scalars and vectors this time. And we've added to the learning goal, and I realized that the second goal should have been added to the previous lesson as well. So we're adding students perform operations on vectors in 2 space and 3 space and use the properties to solve problems. All right, when you're multiplying a scalar k by a vector a, it can change the magnitude and the direction of the vector depending on the value of that scalar. So if the value of k is less than 1, the magnitude of the vector will become smaller. If k is greater than 1, the magnitude of the vector will become larger. And if k is positive, the vector will stay in the same direction as the original a. But if it's less than 0 or negative, the vector will have the opposite direction of the original a. Of course, if k is 0, then 0 times the vector is the 0 vector. We're also going to define collinear vectors today. So 2 vectors u and v are collinear if and only if it is possible to find a non-zero scalar k such that u equals k times v. Essentially, collinear and parallel are interchangeable. So you can make use of either one of those terms here. So collinear and parallel. The one place you'll see collinear where you won't see parallel is in the discussion of points. So you may see a question where it says these 3 points are collinear, but you would never hear someone say these 3 points are parallel. And then of course we also have unit vector to be in use this time around, and that would be a vector with a magnitude of 1. So here we have an example. The vectors x and y are unit vectors, and they make an angle of 30 degrees with each other. So remember here that when you're drawing these diagrams, we want you to use a ruler, because we want you to be as accurate with your scales as you can. And also to estimate your angles as best you can, especially noticing obtuse versus acute, so that your answers make sense in the end. And of course the angle between these is 30 degrees. So that's kind of our setup to begin with. We have these 2 unit vectors, and there's 30 degrees between them. We want to first determine the value of the magnitude of 3x minus y. I guess we need to label which one's which. So we'll call that x, and that one will be y. So 3x, so we need x to be 3 times the length. And again, this is why you're going to use a ruler. And then we're subtracting y. So y needs to be a unit length, and we're going to subtract it. So we have 3x and negative y, and notice the negative y's tail is at the head of 3x. And of course, because the angle between them was 30 degrees, you can see that this angle here is also going to be 30 degrees. And we are looking for the resultant vector. That goes from the start of 3x to the end of negative y. So this guy here is our 3x minus y. And we want to know the magnitude of that guy. We can see that we know the magnitude of the 2 other vectors and the enclosed angle. So this has set up our cosine law for us. So magnitude of (3x minus y). We'll fill that in with our cosine law. So we'll get 3 squared plus 1 squared minus 2 times 3 times 1 times the cosine of 30 degrees. So we have 9 plus 1 is 10, minus 6 in cosine 30 is root 3 over 2. So this is 10 minus 3 root 3. And of course, we actually want the magnitude, not the square of the magnitude. So this is actually the square root of this guy. So there's our magnitude to answer part A. And for part B, we want to know what's the direction of this guy. So you can see that all we really can do is the direction relative to one of the vectors we already have. So we're going to describe the direction relative to the direction of the vector x, which means we want to solve for this angle in here. So we'll call that theta. And now you'll see we know all 3 side lengths and we're just missing an angle. So we're going to use sine law here. So for part B, sine theta over the opposite, which is 1, is equal to the sine of our known angle, which is 30, over its opposite, which is the side length we just found. And then we'll have to do a little bit of rearranging, but because sine theta is over 1, it's a pretty simple one. So we're going to take the inverse sine of this value. And throw that into your calculator to get a final answer, which when we round to the nearest degree gives us 13 degrees. Okay, second example. Given the magnitude of u is 3 and the magnitude of v is 5 and the angle between our 2 vectors is 120 degrees, we want to find the unit vector that's in the same direction as u plus v. So we first need to start ourselves off with a diagram. So we've got a u and a v, and again you're going to do this with a ruler so that you can be accurate with your lengths. And this here is 120 degrees. So we can imagine turning this into a parallelogram. And so my resultant vector u plus v will be that one. And because this is a parallelogram, we can conclude that this angle here has to be 60 degrees. And so we will use our cosine law to find the magnitude of u plus v. which will be 3 squared plus, ideally you should fill in your formula here with the variables first and then fill it in. I'm doing this to save time and also because this pen is really annoying to use. So 3 squared plus 5 squared minus 2 times 3 times 5 times the cosine of 60 degrees. And so we get 9 plus 25 minus 2 times 15. Cosine of 60 is a half. So we have 9 plus 25 is 34, minus 15 is 19. So the magnitude of u plus v is the square root of 19. And so since we want the unit vector of this, we don't want the magnitude to be the square root of 19, we want it to be 1. So that means that our unit vector will have to be 1 over root 19 of u plus v, because that'll make it have the magnitude of 1. And of course, that will turn out to be the same as 1 over root 19 of u plus 1 over root 19 of v. This is using what's known as the distributive property. And here's a quick summary of those properties. So there's the distributive property that we just mentioned. So you've got the distributive property there. The commutative property we brought out in the previous lesson, right? The idea that the order can be reversed of your addition. And the associative property we haven't actually explicitly stated, but it works for this as well. We're going to, here's a quick little thing for distributive property. Let's say you had a plus b. Sorry, I'll switch back to the actual pen there for you. So we have a plus b, and let's say we want now 2 times a plus b. So now our a needs to be twice as long, and our b needs to be twice as long. And you can kind of see from my rough drawing that the answer ends up being in the same direction and is twice as long. So that's your distributive property. And the associative property we kind of saw last time, just not mentioned explicitly. And that's in the very last one we did when we did OF. OF can be determined in multiple ways. For instance, you could have done A plus C plus B to get there, but we also could have done A plus C plus B directly. So right, that would be kind of giving yourself the brackets, but you could also reverse the order of the brackets and have done something more like this, where you're doing A plus C and then plus B. Right, so all of those things get you to the same answer. That's your associative property.